Greetings to you. We will continue our discussion on the potentiometric titrations. Earlier we had discussed how the potential measurements can give you equivalence point at the sharp equivalence point for acid base titrations and precipitation titrations. Redox titrations also can be done very easily, and I had told you in my last class that reactions involving complexation exhibit slightly more complicated titration curves because of the different ionic species that are formed in the chemical reaction. Best example is silver. Silver will react with silver cyanide to give you a precipitate. If you add more cyanide, it will dissolve. The precipitate will redissolve, and then you will get silver cyanide AgCN twice minus complex. So, near the start of this titration, silver cyanide ions are formed. Why? Because we are taking cyanide in the beaker, okay, and so we are going to add silver from the top. You understand? Normally, we do the silver cyanide titration taking cyanide in the beaker in the bottom conical flask and adding silver from the top, so that we do not waste silver solution. Silver is costly metal. So, near the start of the titration I have only cyanide solution at the in my conical flask. There I am going to add a few drops of silver. So, cyanide will be more and silver will be less. So, silver cyanide will be forming a complex instead of a precipitate. So, at silver initially silver cyanide AgCN2 minus ions will be formed and AgCN2 minus ions are soluble. No, you will not see a precipitate. As you keep on adding more and more silver, the ratio of cyanide and silver will keep on changing. So, once it changes and silver will keep on increasing, cyanide will keep on coming down. When they become equal, concentration of silver and cyanide will be same. At that time precipitation will start. So, that is the basic chemistry of the system. So, at the completion of the reaction, potential of silver chloride silver electrode shows a sudden decrease, after which the insoluble silver cyanide will start precipitating. So, when all the cyanide is used up, another jump in the potential will occur, because the silver ions will be more. So, PAG will keep on increasing. So, other examples of complexation titrations include, you can do silver cyanide, silver iodide, silver bromide, silver chloride, silver thiocyanate, and any other precipitation reaction you can do, but most of them should be sparingly soluble salt. So, first equivalence point in this reaction silver cyanide, silver cyanide will correspond to that species for which the solubility product will be lowest or highest. It will be highest. Okay. Solubility product is higher, and that will precipitate first, and then it will react with iodide, because the next solubility product next higher would be iodide, slightly lower than cyanide, third will be bromide, fourth will be silver chloride, which will be minimum soluble. Okay. So, if we remember all those things, one can really plan for the transfer of the silver cyanide, bromide, iodide complexes, etc. Now, we will consider a little bit about the oxidation redox reactions. So, redox reactions are also followed by a simple platinum indicator electrode and SCE, that is saturated calomel electrode. consider a reaction of stannous chloride with ceric sulphate. So, I can write the reaction something like this: stannous SN2 plus is stannous, will react with ceric ions to give you stannic ions and cerous ions. Okay, so, I have two cells, one is stannous stannic, another is cerous ceric. Okay. So, it is like a concentration cell now, because I do not have a tin electrode, I do not have a cerium electrode, both of them would be platinum electrodes. Okay. So, in the platinum electrodes I have two beakers, one is stannous and another is ceric cerous system, or I can take in one beaker add ceric solution in that. So, the equilibrium constant for this reaction is given by K is equal to SN4 products divided by reactants, that is the equilibrium constant. So, I write SN4 plus Ce3 plus whole square divided by SN2 plus multiplied by Ce plus 4 Ce4 plus whole square. Okay. So, at the start of the reaction, the ratio of stannic to stannous is nearly 0, is not it? Because I am taking stannous, I have not added anything. So, most of it is in stannous. So, stannic will be 0. So, SN4 plus is 0 divided by anything is 0 only. So, at the start before I add anything, SN4 plus by SN2 plus ratio is nearly 0, and log of SN4 plus by Sn, logarithm of this entity has a large negative potential, it is not easily determined at all, some very high number. Okay. Then after the first addition of the oxidant, that is ceric, some stannous is converted into stannic and the potential is given by the half cell potential E is equal to E naught of stannic to stannous, that is standard reduction potential of tin system available from database, plus 0.0591, it is a 2 reaction system. So, 0.0591 divided by 2, then logarithm of stannic to stannous, products divided by reactants. See here the product is SN4 by SN2. Remember, we are considering only stannous system, not ceric cerous. So, for the half cell corresponding to stannic stannous, we write this reaction. Then after some cerium is present, we add a little bit, and then what we have? We also have another system where ceric cerous also will be present, because we have added ceric ion that is used up for the reduction, for the oxidation of stannous. So, ceric cerous also will be complementarily available the moment you add the first drop of the ceric cerous solution. So, I can write equally another reaction, that is ceric 4 plus E naught ceric cerous plus 0.0591 logarithm of Ce4 plus by Ce3 plus. Now, what do I have here? The problem is, it is a single electron transfer system, ceric to ceric 4 to 3. So, I have to divide this by only one unit, 0.0591 divided by 1. So, I do not choose not to write 1. Okay. So, this ceric cerous system is given by this equation. Okay. Now, as it is a concentration cell, both of them are in solution. I have only the one of them is platinum electrode, another is it may be another platinum electrode or it can be reference electrode. Now, as the platinum electrode cannot have two potentials, the E value has to be identical, whether it is steric serous or stannous stannic stannous. The potential for the single electrode has to be same, because all of them are there, it shows one potential. It does not say first I will show you stannic stannous, then I will show you steric serous. No, nothing, it will not work like that. All species are there. For all the species, that is the EMF value you get. That is same for stannic stannous, you can take it for steric serous also. So, what I have here, the E values, they have to be identical. So, I can write E naught steric serous plus E naught stannic stannous would be equal to 0.0. I can combine actually I am combining the previous two equations, this equation, these two equations. I write 0.0591 by 2 logarithm of stannic by stannous minus E A minus E B. This is what I had taught you in the beginning. So, the cell voltage would be the sum of the difference between the two, that is sum of the reduction potential or sum of the oxidation potential. One would be minus anyway. So, one would be reduced, one would be oxidized. So, I can write a reaction something like this, SN4 plus by SN2 plus minus 2 times log of steric to serous. Why this 2 here? Again it is a single cell reaction, but requires double the concentration. It is a because stannic stannous there is a change of 2 valence state, here it is a change of 1 valence state. So, it has to be twice the stoichiometry. So, I can write this equation can be rewritten like this, 0.0591 divided by 2 logarithm of stannic by stannous into serous by steric, both of them should be whole square, it should be 2 here in the steric also. There is an error here, I will take a look at it later and correct it, but for the time being this is consider it as a, please make in your notes correction 2 here, and this expression stannic stannous multiplied by serous steric whole square is nothing but the stability constant log K. So, I can write 0. The difference of the EMF should correspond to 0.0591 by 2 multiplied by logarithm of K, that is equivalence point, equilibrium constant. So, I know the values of the stannic stannous and steric serous. Here I am writing E A minus E B, okay. That is both the cells EMF I know. So, 1.61 that is for steric serous and 0.15 is stannic stannous and 0.0591 that is equal to log K. So, our K is equal to anti-log of this number, that will be 2.5 into 10 raised to 49. So, what do you deduce from this value? K is equal to 2.5 into 10 raised to 49. Equilibrium constant for the reaction stannic to stannous plus steric to serous is 10 raised to 49. 2.5 into 10 raised to 49. What do you deduce? What does it tell you? I will give you 3 seconds, think about it. Okay. If you have got it right, you are a good chemist, you have understood the principles. If you did not get it, here is the answer. an equilibrium constant of very high value, approximately more than 10 raised to 2, 10 raised to 3, anything above that indicates that the reaction is totally complete, virtually complete. So, that you should remember. Any equilibrium constant, if it is high, that means the reaction is proceeding towards the right, whichever way you write the equation. Okay. So, we understand that the value of 2.5 into 10 raised to 49 means all the stannous is converted into stannic using steric ions, that is a redox reaction. Reaction percentage more than 100%, not more than 100%, but it will be almost 100%. So, at the equivalence point I can say that the concentration of Ceras Ce3 plus should be twice that of stannic, because it is a two electron system. One molecule of Ce3 plus will react with 2 molecules of other way around, 2 molecules of Ce3 plus will be reacting with Ce4 plus will be reacting with 1 molecule of stannic to give you 2 molecules of stannic, and the quantity of Ceras should be equal to twice that of stannic concentrations. So, Ce4 plus also should be twice that of stannous. This is oxidant, this is reductant, reduced species. So, this would be like this, and stannic to stannous would be the total number of ions would be 2 of steric and 1 of stannic. So, 3 molecules are there. So, the ratio of stannic to stannous should be equal to Ceras to steric. This is oxidation, this is reduction. So, I write the reduced species on the numerator and oxidized species on the denominator. So, stannic to stannous ratio should be equal to Ceras to steric, and so the equilibrium constant for this reaction is given not by square root, but by cube root. Three species are there. So, the K value we know is 2.5 into 10 raised to 49 here. Okay. I take the cube root, that means how much I am getting? 2.92 into 10 raised to 16. What does it tell us again? I will give you 3 seconds pause, maybe 5 seconds pause. You must consider this reaction and find out, tell me what does it mean. Okay. If you have guessed it, well and good, otherwise here is the answer, that is the ratio of stannic to stannous is same as Ceras to steric, that is number 1 point. Number 2, the ratio is 2.92 into 10 raised to 16 for any of these. We can now substitute the value of these ionic ratios in the equation, Nernst equation. This is for stannic stannous. E is equal to 0.015, this is E naught SN4 plus by SN2 plus 0.0591 divided by 1 log of oxidant divided by reductant. But we know that stannic to stannous ratio is 2.92 into 10 raised to 16. It should be 16, huh? Yeah. Again there is an error here, I should correct it. So log of 2.92 into 10 raised to 16, multiply it by 0.0591 and add 0.15, this reads to 0.64, and because the EMF cannot show one value for stanic stannous and another value for spheric cirrus, we should get the same value for spheric cirrus also. Whether I calculate it for stanic stannous or spheric cirrus, I should get the same value. Now you check this. The E naught value for spheric cirrus is 1.61, and here I am writing minus 0.0591. Find out why I write minus here and plus here. Okay. That is an exercise for you, and this minus this into log of 2.92 10 into 10 raised to 16, that is understood. That also would give you the value of 0.64. This is a thumping corroboration of the theory what we have been talking about. Okay. So, either way, whether it is stanic stannous or spheric cirrus, we get the same potential. That is what we want anyway, that is what we expect. So, the same value is obtained both ways, which is expected. So, many redox reactions, especially those with permanganate, dichromate and nitrate and other similar oxidants, have a strong dependence on the pH, and the potential calculations become slightly complex. What does it mean again? Again I will give you 3 seconds pause to try ask you to digest this information on this paragraph. Many redox reactions, especially those with potassium permanganate, potassium dichromate, nitrate and similar oxidants, have a strong dependence on the pH. So, what does it mean? That means the equation what we have written here, E is equal to E naught plus RT by NF log of some concentration of the oxidant divided by reduced species, this number will be influenced by the pH, that is whether you carry out the reaction in acidic medium or basic medium, or what should be the pH. If it is 4, you will get some value. If it is the pH is 5, you will get some other value, like that. So, there is no clear indication to calculate what is the expected EMF for a reaction which is pH dependent. Okay. So, you can listen to this lecture again and again and find out what exactly I have said just now. So, in general it should be good for you to understand that the reactions would be fairly comfortable if you understand that the pH interactions are important. They can affect the ratio of the oxidant to reduced species, and we cannot write the actual equations involving the standard reduction potential as obtained from Google or database, other databases. So, we will have to actually carry out the reaction at different pH and then determine the EMF what we get. Okay. So, for example, in the permanganate titration of iron, the equilibrium constant is given by this expression. Look at this, K is equal to Fe3 plus raised to 5 and Mn2 plus, that is the reaction concentrations of the products, divided by ferrous raised to 5, MnO4 minus raised to 1 and H plus raised to 8. That means, the reaction is very highly dependent upon acidic medium. This reaction will go that is oxidation of ferrous to ferric using potassium permanganate will go only if the reaction is strong, if reaction media is strongly acidic, otherwise it will not go, it will be very slow. So, the EMF also will be different. So, at the equivalence point K is equal to ferric by ferrous, should that also should be equal to oxidant by reductant. So, what is the other system? Mn2 plus divided by MnO4 minus. Okay. So, this comes here, the total species is 5 here, 1 here. So, it should be 6. So, the for any species the concentration equilibrium constant concentration ratio of the oxidant to redox should be 1/6 of the equilibrium constant, total 6 ions. So, K raised to 1 by 6 into H plus raised to 8, that is the chemical reaction, and then 5 electron system. So, divided by 5, 8 by 5. So, the equilibrium constant K is that value, then take 1/6 and then multiply it by H plus raised to 8 by 5, you will get the ratio of ferric to ferrous. Now, look at it. What is the reaction basically? I have MnO4 minus plus 8 H plus, that is a highly acidic reaction, plus 5 electrons, that will lead to Mn2 plus 4 H2O, and 5 Fe2 plus, this other half cell reaction goes to 5 Fe3 plus 5 electrons. Okay. So, E is equal to E naught plus 0.0591 divided by 5 electron system, logarithm of MnO4 minus into H plus raised to 8 divided by Mn2 plus. This should be equal to the redox potential of this system E naught 1.52, remaining concentrations etcetera will remain the same. And we also have another system, that is one previous one was for MnO4 and Mn2 plus, and now another system that is prevalent in the same beaker is ferric ferrous. So, I write E is equal to E naught plus 0.0599 for 059 divided by 5 logarithm of ferric by ferrous raised to 5. So, if I again E naught value is known 0.77 and 0.059 by 5, this remains the same. At equilibrium I can write the left hand side manganese manganate is one's half cell, the potential should be equal to ferric ferrous, that potential. So, for manganese reaction, manganese manganic reaction, the E naught is 1.52 plus this, and I can write equivalent iron system. And if you take a look at this system, you can separate the numerical terms 1.52 and 0.77 on this side, and this part you can transfer on the other side and rewrite this equation. So, what do I have? Logarithm of Mn2 plus and Fe3 plus raised to 5 divided by this MnO4 minus into Fe2 plus raised to 5 into H plus raised to 8 should be equal to 5 into 1.52 minus 0.77. This is the E naught values. Okay, there is no magic there, divided by 0.0591. Okay. So, that will be 63.5, that value. So, K is equal to this value divided by this value. So, how many species are there? Again 3, because MnO4 and Fe3 plus, Fe2 plus, one oxidant, one reductant and H plus. So, there are 3 species, complicated reaction. So, the again K value, what is the K value? K value is 3 into 10 raised to 63. You just solve this equation, you will get 63.5, convert it into logarithms, anti-logs. So, K is equal to 3 into 10 raised to 63. This large value shows that the reaction is virtually complete. That means, in presence of acid, you can reduce all the hydrogen, all the iron, ferrous to ferric. And what is the oxidant here? Potassium permanganate. So, from the equation, large value of K, we can try to decide how to do the titration. I can take 10 ml of 0.1 molar potassium permanganate and 0.1 mole of ferrous sulphate. So, then Fe3 plus would be 0.01 normal at the equivalence point, and assume that we are using only 100 ml. So, Mn2 plus would be 1 over 5 Fe3 plus, that is equal to 0.002 normal, and Fe2 plus would be x, that is unknown. Why? Because whenever I am trying to remove ferrous as ferric and the reaction is almost complete, virtually complete with a K value of 63.5, the reduced species would be very low in concentration, very negligible. That is why we are writing Fe2 plus as negligible, it is a small quantity x, we are writing like this. But Mn2 plus, I know what is the concentration, ferric I know what is the concentration, ferrous I do not know the concentration, how much is unreacted, because the reaction is virtually complete. So, very small quantity, we cannot determine that. Okay. So, let excess of permanganate solution at the equivalence point be 1 drop. Okay. So, 0.05 ml 1 drop or 0.05 ml, 1 drop in a burette from a burette corresponds to 0.05 normal ml. So, I can write 0.05 ml and then 0.1 is the concentration, total volume is 100 ml, the concentration of ferrous would be 5 into 10 raised to minus 5 normal for that 1 drop excess, and that also should be equal to manganese permanganate ion, MnO4 permanganate. So, ferrous would be equal to manganate ion, because all the permanganate has been used up in the oxidation, very less of the oxidant will remain at the end of the reaction when you add stoichiometric quantities. So, using the same analogy, ferrous to ferric, manganese to mannic, whatever is ferrous should be equal to oxidant of the other system, and whatever is reduced system should be equivalent to oxidant of the reduced species of the other system. So, we submit the values in this equation. K is equal to 2 into 10 raised to minus 3 multiplied by 1 into 10 raised to minus 2, this is for ferrous, and this is for the MnO4 minus and x raised to 5 into H plus 1 molar acid 1 raised to 8. So, this works out to 5 into 10 raised to 63 and x would be 5 into 10 raised to 15 minus 15, that means the reaction is again virtually complete. There is no more ferrous to be reacted. That is why whenever we want to oxidize ferrous ion, we take potassium permanganate and oxidize it. So, we are going to consider a redox reaction of titration of 100 ml of 0.1 normal ferrous ion with 0.1 normal ceric ion in presence of sulfuric acid using ferric ferrous electrode and ceric cerous electrode. We will study this reaction. The actual reaction can be represented like Ce4 plus and Fe2 plus goes to ceric and ferrous. This is a very standard reaction. Okay. So, we will continue studying this reaction in the next class and then move on to polarography after that. So, thank you very much. We will meet again.